Hi class, this is Mr. Morris, and I wanted to go through a few examples of the different molecular geometries or the different shapes that we can have, and how to determine whether it's polar or non-polar. Now, with all of the examples in this table, we're assuming that the atoms on the outside, so our outer atoms, are the same. So that's an important concept. If any of those atoms were different, then they would automatically be polar. So let's say, just looking at this example down here, if one of those was not chlorine in PCl5, if one of them was not chlorine, but let's say it was fluorine instead, it would automatically be polar because we would have a different electronegativity on one side. One of those atoms would have a different electronegativity. This next one, the SO2, has an important point that I want to get to. So often students will look at a molecule like this and they see the lone pair of electrons and they think, okay, well, we've got a lone pair. That must mean that this is the negative side because we have electrons. That's got to be the negative side. That's not actually necessarily true. Now, part of the reason is because we have electrons around the other atoms too. What we really have to look at is the electronegativity of the elements in it. And if you found sulfur and oxygen on the periodic table, you'd find oxygen is just above it, which means oxygen is more electronegative. So if we wanted to figure out which of those was more, or which way our dipole would face in these bonds, it would face toward oxygen. And it's important that you think about the shape when you decide if something's polar or not. See, oxygen's more polar than sulfur is, so we've got a dipole pointing that way. And if it was linear, which is kind of what it looks like here, then those dipoles would just oppose each other and they would cancel each other out. That's not really what's happening because it's a bent shape. So our dipoles, got two of them, and if you were to add them together, they point down. Okay, so if we were to add those two dipoles together, they point downward. So that makes this polar. All right, let's look at another one, CH4. Well, we've got four dipoles. Hydrogen is less electronegative than carbon, so they would point this way, that way, and that way. And they're all pushing towards the middle. The electrons are all moving toward carbon at the same magnitude. So that means that these dipoles all cancel out, and that makes this a non-polar molecule. Now we've got NH3. Again, that lone pair at the top, it doesn't tell us that that's where the electrons, that's the more negative atom necessarily. It might not. But what it does tell us is that the other bonds are going to bend away from it, and that changes the molecular geometry. Instead of being trigonal planar, it's trigonal pyramidal, which you can see here. Hydrogen is less electronegative than nitrogen, so our bonds are going to point this way, and this way. And if you were to add those bonds all together, they're going to point upward. So we've got an overall dipole that points upward. That makes this a polar molecule. And then we've got another bent molecule. Now, bent molecules are almost always going to be polar. Let's talk about why here. We've got our dipoles pointing that way and that way. And if you add them together, they point straight upward. So that makes it polar. We have a net dipole. All right, now we've got trigonal bipyramidal. Phosphorus is less electronegative than chlorine, so we would have a dipole facing out towards each of those chlorine molecules. But if they're all pulling with equal strength and they're spread out evenly or equally, then they are going to cancel out. Their dipoles will cancel out, and that makes this molecule nonpolar. The next one, however, SF3, because we've got one of those electron areas that's a lone pair, we've got a dipole going that way, and a dipole going this way, a dipole going this way, and another dipole going this way. Some of them cancel out, but those two on the x-axis add together and point to the right. So that makes this a polar molecule. Our T shape, very similar. Got a dipole that goes this way, and this way. You can see that these two cancel each other out, but this dipole has nothing to cancel it out. So this one has a net dipole that is still pointing downward. This is a polar molecule. All right. XeF2, F is more electronegative. You can see that these two dipoles cancel each other out because it's linear. So this is nonpolar. Looking at the octahedral molecule, all of our dipoles, there are 6 of them, and they cancel each other out, so that makes this nonpolar. All right, BRF5, well, all of those in the square base cancel out, but there's one more going up. That gives us a net dipole pointing up, which makes it polar. And then finally, XeF4, these dipoles all oppose each other, cancel each other out, therefore it's nonpolar. All right, that's it for just kind of looking at the geometry of these and deciding which molecules would be polar, which would be nonpolar. It is an important skill to be able to decide if a molecule is polar or nonpolar. You'll find that it becomes really important in our next unit, which is talking about intermolecular forces.